sigma 2 pi r squared. Sigma here is the surface charge density, which is just my charge of my sphere, Q sub s, divided by the surface area. So sigma is the charge of the sphere divided by the surface area, which we established earlier was 4 pi r squared. So if I plug that in, I now have j hat k sub c over L squared, big Q, 4 pi big R squared times QS over 4 pi R squared. Wait a second, I can cancel some stuff out here. Who would have thought? That cancels out with that. And what I'm left with is that the force on Q that's sticking outside the sphere there is going to be the Coulomb's constant times Q, the charge outside, times the charge of the sphere over L squared, J hat, which looks a whole lot like Coulomb's law. Now, we went through all of that, came out with a simple answer. What this means is that if I have a charge with spherical symmetry, and I am outside of that, then I can treat this like a point charge sitting right there at the center. That will be a useful thing to do many times. Or we set up a lot of problems where that is a useful thing to do.
We kind of hand waved that in 152.
Absolutely.
Yeah.
And I just did that with the previous class I had before here is 152, where I hand waved it and I just.
So we
Or
don't
like
need
just
to
give me
use
an
any
out.
of this. This is just to show why we can use it as a point charge. It's just
Yes.
proof.
Because I was sitting here thinking for a hot minute, I was like, whoa, these tests are going to be brutal.
Well, they still might be, but that's not. All right. So, one other thing. If we pick a point inside, the only thing that changes are the limits of integration. So if we are inside, let's say we are here, so L is less than big R, the shortest distance is going to be that, which is L minus R, sorry, R minus L. And the longest distance will be R plus L. So the limits of integration would change to R minus L, and that's still L plus R.
That works for both a hollow sphere and the uniform density sphere.
Sort of. We will use this concept to apply to if we have an insulator with charges distributed throughout.
Or if it's like a metal ball. Like a-
If, I'm sorry, if it's a conducting sphere, all the charges on the outside, yeah, you'll use this. If it is an insulated sphere where the charges are distributed evenly throughout, if I'm outside of that, you still treat it like a point charge, because it's still a spherical symmetry. If I'm inside, it gets a little bit different. So my limits of integration, so this now becomes R minus L, R minus L. This becomes R, sorry, that's the same. This becomes R minus L. This is R minus L. R minus L, so that becomes negative there. And here, the R's cancel out, and left with 2L. Here I got negative L, negative L, negative, and then an R minus R. So then it ends up being 0. If I have a shell with uniform charge density, if I am inside the shell, if I have a charge inside this shell, the force line is 0.
force outside of it.
Wait, say that again?
So if I got my shell here, uniform charge distribution. If I'm outside, I can treat this like a point charge at the center. If I'm inside, there's no force acting on the charge on the inside.
Why?
Well, the math works out. I mean,
More intuitive understanding from my perspective is that if you have a point in the sphere at any point, then you're just gonna have a force that's gonna move it into its center. We're just gonna have all the forces acting on it, so there's no.
a little bit off of that, if I'm on the inside, if there's no force on it, it won't be forced through the middle. So if I'm on the inside, if I'm here, I'm gonna have forces pushing in all directions. The ones over here it's much closer to them, so this is gonna be a much greater force, but I have fewer of them. I have a lot more forces over here, but it's gonna be a weaker force, but it balances out. More forces are, more charges exerting to the left, but with a weaker amount each. Fewer forces here, but a greater each.
And it doesn't make a difference whether they have the same charge or not?
It does not. I thought that was different than what you had just said.
Yeah. My perspective was it would eventually move to their center, because I wasn't considering, that the forces weaken over in space. If that makes sense.
Oh, okay. All right, on that note, class has ended. I've got another one in 2 minutes. Sorry, Tuesdays are gonna be like this. Thursdays, I got a gap of an hour and 15 minutes, so it's like 15 minutes.
A hollow sphere, the charge is distributed inside and the outside?
It turns out if it's a conducting sphere, they'll be on the outside. And we'll get into some justification of that. First one. No, the first plan is due Friday. The homework, I will eventually have a piece of paper on the wall, which gives me due dates on blackboard. Yeah, the due dates on blackboard, I had to put in something. And so they are. Those dates are changing.
It wasn't really hard.
Set up that.
He said, it's just like.